Cool. So today we have Alex talking about hyperbolic geometry or non-Euclidean geometry.
Non-Euclidean. I like do a mix, but I mostly focus on spherical and elliptic, just because that's like what my background and understanding is mostly in.
Cool.
Let me get this.
And then we have Kalachi from Brooklyn Kalachi. So if you guys, if somebody wants to call Rita, she can also get one.
Which ones are these?
I don't know. I don't know what flavors there.
I think I'll take this one.
One of them is peanut butter and jam. That one's mine.
That one's blueberry sweet cheese.
This one's sweet cheese. Okay, I can't have cheese. Sorry,
It
we're
also
just
looks like sweet cheese. That's probably that one.
All right, cool.
That one
Wait,
she's
oh,
upside
wait,
down.
no, wait.
That one looks
That
about
one looks like,
correct.
All right, great.
I don't know.
We'll take
What
this
is
one.
that?
This one looks like the strawberry rhubarb one.
All right, man, it's all you.
You guys see the screen?
Yeah.
Perfect. Okay, so I am going to be sharing with all of you about non-Euclidean geometry. A good part of my understanding of this is from a math course I took, and so credit to Dorian Goldfeld for that instruction. But yeah, I'll go ahead and get into it. Oh, and if anyone has any questions, what?
Is that a Columbia class?
Yeah, it is. It's officially called Making Breaking Codes, and then it's like a cryptography class. And there's like a case study that I did in here. But yeah, anyways.
Cool.
And if anyone has any questions, feel free to like stop me whenever, in case I like go over anything too quickly. How do I? Okay, so to give a brief overview, there's two like primary types of non-Euclidean geometry, and those are elliptical and hyperbolic. And the basic premise of like where these come from is if you take, instead of a plane, which is 2D, and you basically base your geometry on a more three-dimensional system, such as a hyperbola, a hyperbolic surface, or an elliptic surface being a sphere. A lot of the basic premises of math start to change a lot, but there's some interesting implications in terms of physical geometry, but also within modular arithmetic. And so I thought some of the most interesting things about elliptic geometry are that there's no parallel lines and there's also no similar triangles. And like, if you try to like rationalize that, it's basically because on a sphere, like neither of those things are possible. And so a lot of the math rules start to very quickly change. And so I'll get into it a little bit more here. Oh, and another thing to note, I thought this was interesting as well, is that like in an elliptical space, the angles of a triangle are greater than 180, whereas on a hyperbolic surface, they're less than 180, and that's due to the curvature of the surface, which is just interesting to note. So some basic implications just here. So like the Pythagorean theorem changes really quickly. And then I've also included the distance formula here because distance on a spherical plane and on a hyperbolic surface are also a lot more complicated than doing that on a two-dimensional plane, and basically involves calculating. There was some advanced derivations for like where these came from, but I thought that it was just interesting that they both depend on like trigonometric functions instead of just like strict algebra.
There's a is there like a magnitude term that's missing for the for both the spherical and the hyperbolic Pythagorean theorem? Because like cos A, cos B equals cos C. Cosine is between between -1 and 1.
Sure.
So
I had not thought about that. I guess theoretically there should be. I guess if you get a negative distance, then like you would just obviously correct that. Yeah, I guess that's a good question. But yeah, I'd assume if you get something negative, then you'd probably just correct that to positive to allow for,
And for the distance formulas, sorry, one other question. For the distance formulas, are the U and V vectors or are they points?
No, U and V are vectors.
Okay. Cool.
And then in terms of like conceptualizing this, I know it's like, I guess at least for me, it was kind of difficult to like wrap my head around just how you would like handle these surfaces. And so a lot of mathematicians have like put a lot of work into like projections. So these are like images of Poincare's hyperbolic disk, which basically models a hyperbolic space in a two-dimensional disk by projecting that down. And then basically the arcs come from like overlapping circles that like come into contact with the outside disk. And then the distance formula is given by another formula here. I thought it was very interesting that like this this image on the right here shows really well why hyperbolic and elliptic geometry lend themselves really well to modular math. And so that's the basis for a lot of cryptography because like basically there's a lot of patterns in the way that numbers repeat and that like large mod spaces can be quickly calculated using this arithmetic. In terms of like some very general applications before I get into like the specific case study I want to do today, which is focused on like cryptography, I guess the like very intuitive application is in like physical spaces. So, you know, obviously if you have like a hyperbolic or a spherical shape, then this applies. The ones on the right, a lot of the like theories surrounding or like where these models of geometry came from is from like when they were trying to determine the shape of the universe. So a lot of math is related to that. And then basically whether there's positive or negative curvature to that plane. And then this is just from a recent article in Science that I read that was about like the shape of biology particles. And basically just cellular structure is very heavily oriented around spherical structures. So I thought it was just an interesting example of like where this is encountered. So the case study that I want to get into today is elliptic curve cryptography, which is used by like a number of, it's used in conjunction with another of other cryptography schemes, and really illustrates why elliptic curves and elliptic non-Euclidean geometry is useful. And this one I thought was a little bit less intuitive just because it like kind of comes out of the way that elliptic curves work with modular spaces, and so it's not really like a physical manifestation or anything like that. And so the basic definition of elliptic curve is just given by, you know, the set of points satisfying an equation of this form. And when we do math with elliptic curves, we assume that like that the addition and the subtraction and like basically all point operations are going to be redefined because we're working with elliptic curves and not with like a typical Euclidean geometry space. So this is the basic definition, and if anyone has any questions. Yeah, this is just basically the definition of a elliptic curve without the mod space. And so like part of the interesting thing is that a line going through 2 points on an elliptic curve and another, basically all of the typical arithmetic with tangent lines or other individual math operations gets a lot more complicated because we're not strictly working with Euclidean geometry anymore. And so in order to find a line going through 2 points on an elliptic curve, you basically substitute based on the original equation, which is very similar to like linear arithmetic, but that when you plug that into Euclidean, to elliptic curves, you wind up with a more complicated formula. And then from here, these final figures down at the bottom will eventually lead to the addition formula for points on an elliptic curve. So another similar thing is finding like a tangent line to a point on an elliptic curve. And so for this, you just take the derivative of to find the slope of the tangent line, which, you know, makes sense given how you typically intuitively expect that to go. And so in order to get the third point of intersection, you basically just substitute back in as we saw before. And so this is where in elliptic curves, the addition formula is calculated by finding the line between 2 points, finding a third point of intersection with the elliptic curve, and then reflecting that over the x-axis. And so finding a tangent line to a point on an elliptic curve, and then also a line between 2 points is critical in doing like a lot of more complex operations. And so using this, you can basically derive x3 and y3, which will give you a third point of intersection. And so when we move into elliptic curves mod p, this is where like this really becomes more about cryptography. And part of that is a lot of modern cryptography is based on the generation of large primes to use in key exchanges like Diffie-Hellman and RSA. And so similarly in elliptic curve cryptography, this is dependent on having some prime p to define the mod space. And typically these primes are like, since the like security of the encryption scheme is heavily dependent on how like unfactorable that prime is, or basically dependent on how large the entire crypto scheme is very dependent on having a very large prime. And so there are like companies that just spend like that basically calculate large primes as like their primary product. And yeah, I guess the key thing to note about mod p is that these are typically like 100-digit or even like 200-digit primes that are just like very, very large, that the computational power to like calculate over the entire mod space is just like basically too large for anything but a supercomputer. And so that basically ensures that no one's going to break the crypto scheme, because it would take like the computational time of like several billion years.
What's the intuition behind why p has to be prime?
Y has to be prime because if it were factorable, I believe it has to be prime because if it were factorable, then the mod space would be easy to like break down into smaller, like you could basically perform calculations on one of the factors. And so that would be like you could solve for like specific keys or encryption like variables without doing math for the entire prime space.
I see. So just to kind of build my intuition. So let's say I had like 100-digit number that was like divisible by one other factor. That would still be better cryptographically than a really low prime number like 5.
Right. Well,
okay.
Yes and no. I think it depends. If it's divisible by one other number, it's actually a good question. I will like double check on it. But from my understanding, if it's a very large, like it's a large number, but it's divisible by like a single set of factors, but those are both very large numbers as well, then you're much better off than having like a small prime number like 5. The issue more comes if it's like factorable and factors down to like 5 times some other 100-digit number, at which point you're in trouble because like one of them is very easy to solve for.
Got it. Okay.
And so to give you like the formal addition law on an elliptic curve, this is very similar. This is very similar within and outside of a mod space, but here the important thing to note is that mod p is incorporated into these calculations. And
sorry,
so
also, what is a mod space?
So a mod space is defined basically like a mod space is defined by that number p, which here is prime. It doesn't necessarily have to be, but basically like the assumption is that you can only do calculations up to a certain bound because in modular arithmetic, like everything's going to repeat after that.
Okay, so it's like the intuition is like I should think of it like a space that basically a numeric space that exists modulo some number.
Right. Yeah, exactly.
Okay.
A lot of this comes from like, so this comes from, you'll see in like the addition law, and like basically the points in a specific mod space or on a specific elliptic curve form an abelian group. And because that means that there's like a generator, you can basically calculate all of the points on an elliptic curve by repeatedly adding to the generator. And so that will give you all of the points in the group. And so that like becomes very interesting when you get into like trying to do key exchanges.
Got it. Okay.
And so like to try and visualize addition, the other interesting thing is that the identity element is at infinity. And this is because, so basically to try and visualize, you try and, actually the next slide might be slightly more helpful. Yeah, so the way to calculate like the addition of points on an elliptic curve is to find the line that intersects at both points, and then find a third point of intersection along the elliptic curve and reflect that. And so here we see p plus q plus r equals 0, and that's because r is the reflection of some like negative r over here. And so p plus q alone would be some point r that would appear below the x-axis. And then so the additional thing that I wanted to note from this slide is that not only is there an identity element at infinity, but adding p to itself will get you that identity element. And so, yeah, as I was touching upon, points on any given elliptic curve will form an additive group. And so, yeah, this is a better illustration of the way that addition is calculated. But basically, you would take the line through P and Q, find that it intersects the elliptic curve at R, and then reflect that over the x-axis and wind up with P plus Q over here. And then this is like the, then, yeah.
So what if there's no, what if there's no intersection?
So if there's no intersection, then there would usually be, you would basically wind up with the identity element being involved in some way. So for example, so a good example is here where you're adding P to P. There's obviously not a second point of intersection, a third point of intersection along that. And so you wind up with infinity because this like goes all the way up. The same thing is like if you have P at infinity, then you would basically like intersect straight through R. And so you like would reflect it back and wind up with P.
Okay, got it.
And then if you add any points like along here, then your intersection is going to be somewhere up here, even if you add points, because this like is assumed to go up like towards.
Yeah. So like the space of addition is actually like relatively constrained, it seems.
Right, and that's because of the mod space.
Okay.
So the way that like a elliptic curve cryptography key exchange would work is basically most of the information is public. So that includes an elliptic curve, a specific point on that elliptic curve, and then a large prime. So this is the kind of thing that like basically the prime is very important to, like this is what like the Department of Defense or like some corporation that wants to encrypt like any type of like privatized like bank or otherwise privileged information would make that large prime public. And then even the elliptic curve could also be, is also public. And then you can just pick any point on that curve. And so for two people to like perform an exchange over that elliptic curve, the basic way that that's done is, and this can also be demonstrated by choosing like a small alpha and a small beta, but basically Alice takes a private key and calculates the addition of the point Q alpha times, and then Bob does the same thing with some parameter beta, and then after making these figures public, then they both have access to alpha times beta, and then additions of the point Q, but like the public does not have access to that information because they don't have any access to alpha or beta. They just basically like see this as a given point, and without beta, without like the private keys are unable to determine what this like derived shared secret is. And then
Do alpha and beta have to be integers?
What?
Do alpha and beta have to be integers?
Yes.
Okay, and then follow up. I thought we said, so Q is a point on an elliptic curve, yeah?
Yeah.
I thought so we said if you add 2 points together, P 2P is equal to infinity, right?
Mm-hmm.
So adding n. Yeah, so adding n is addition transitive in the way that we would kind of expect it to be, such that we could break this up into like a series of 2Q operations a times, or like a divided by 2 times.
So adding something to like the short answer is no, because like adding like if you did this like 25 times, you're not just going to get the same point back, because like basically if you take a point and like repeatedly add it to itself, you're going to go through all of the points in the abelian group. Like might be easier if I had shown like an addition table, but in short, you're not going to wind up with the same point here. So like if adding 2Q or like adding 3Q would basically wind up with the same point, then like obviously the crypto scheme would not work.
Yeah, I mean, like, well, so I guess I'm trying to like get some into, because like in traditional in non-elliptic curve addition, x plus infinity is infinity, and x plus x plus x plus x can be modeled as 2x plus 2x, which would in this case be infinity plus infinity if the like transitive laws transfer. But it kind of seems like they don't.
No, I believe 2p only like adds to infinity if the point is at let me see. So they also have I should note that here they have 0 as the identity element. But I believe that only holds if P is at this like point of intersection along the y-axis. Otherwise, adding P to itself will basically give you like different numbers.
Okay.
So yeah, this is basically like the way that, or at least like until recently, a large number of crypto schemes were based. And so a good example was like an early Microsoft version where they used this as their elliptic curve, and then gave this point Q as the generator, and then this was their prime number. Yeah, if anyone wants to like do any math with this, I just thought it was an interesting example.
Yeah, let me just like real quick after this.
I have this in here twice. Anyways, I thought there was also a number of like very interesting ways to visualize this, because elliptic curve cryptography, like the way it works as like I showed on in the hyperbolic version of the projection using Poincare's disks, a lot of it is about like these repeating patterns and like cyclic groups. And so I thought that this was just an interesting visualization of the way that like these crypto schemes work by like basically looking for like repetitions of patterns. And then this one is a similar visualization of elliptic curve key exchange. And I believe, so I couldn't read the article on this one because it was blocked by a paywall, but I just thought that it was interesting that like the way they show it is like over this convoluted space, you're looking for points of intersection between or like repeated patterns over a certain mod space. Let me see if I have any more. And then some of the benefits of this are that like elliptic curve has a smaller recommended key size than RSA or Diffie-Hellman. And so like compared to other key exchanges, you wind up with like a relatively more efficient version of key exchange. And this can be done like obviously with certain numbers being public, and then with your two people like Alice and Bob wanting to compute a shared secret, it's a very quick calculation if like for like very rapid transactions. Yeah, I think this is my last slide, but does anyone have any like general questions or like, I guess just like about non-Euclidean geometry? The other thing that I came across that I thought was interesting as well is like there's a whole space of math called taxicab geometry, where like you assume that you can't go between, like basically you have to perform things over the space of a grid and basically can't move diagonally through it, which kind of diverges from like the thought here that like everything is informed by the shape of the plane, but just another like interesting model of geometry that like conceptually has mathematical implications.
We were talking about taxicab geometry the other day, I feel like.
Yeah, we were.
What were you guys using it for?
Well, I mean, because like it's called taxicab geometry because like in a Manhattan grid world, you can't go diagonally.
Right.
And so we were talking about like what the distance was between our like the office and a restaurant that was nearby, basically, which is not super relevant. No, this is pretty interesting. So I guess. So we use hyperbolic geometry and spherical geometry. I guess spherical more than hyperbolic. Like I think we've been calling things hyperbolic, but it's actually spherical in different ways. To like visualize things, right? So like you have like the blob scroller, right? That's basically like applying a spherical transformation onto a Euclidean space.
Okay.
Which I don't know if you've actually played with the current iteration of the app, but like if you've seen the the version that's like public for the Biennale, like that's kind of what it's doing.
Right. Wait, you said that's called the hyperbolic space, but it's actually spherical?
Well, like internally we use words in ways that like aren't correct, basically.
Okay.
Because Jake and I are like not math people, so like, but I think it's like a spherical geometry, not a hyperbolic one. Or at least it seems to like more closely match that kind of curvature, which is interesting.
Yeah, I guess it intuitively seems, because it seems to have like more of a positive curvature than a negative curvature based on like just what it appears like.
Yeah. Like something hyperbolic, it seems like would be like blowing up the edges, right? Like right now, the way it works is like when you hover over something with your mouse, like that area basically gets like a blob underneath it, and like everything is like then projected into a 3D space as if there was like a sphere that's like projected onto. A hyperbolic thing, I guess, would be like the reverse of that, like you have a bowl or something.
Right. What is that implemented using? Like, how is that? Are you like explicitly using spherical geometry, or is that kind of just like a?
No, I think it's a WebGL thing. Like we're applying, we basically have a shader that maps these things to 3D space. It might actually be explicitly spherical geometrically, but like I don't know that we we certainly haven't conceptualized it in those terms, but I wonder if like doing so will actually make things easier for us.
Right. Huh. Okay.
Yeah, this is pretty interesting. I guess I am a little curious. The mapping between cryptography and elliptical curves is really interesting to me. I guess I'm kind of curious, or maybe trying to wrap my head around why this doesn't work in Euclidean space.
So I guess that's funny because when I was like learning this stuff, I was more like shocked that it does work in elliptic space than like because
Like if I squint, I can kind of see like, okay, you know, it has something to do with like the fact that it's modulo p and like that changes the space in this interesting way. But you can apply a modulus to a Euclidean space too, I think. Or like I don't see why you wouldn't be able to.
I guess the important thing here is that the point Q, like if you pick since it's a cyclic group, if you pick a generator, then you can basically repeatedly add the point to itself and find like every single point. Like that'll iterate over every single point in the mod space. And like if you look at a plot of all of the points in on an elliptic curve mod P on a Euclidean graph, which is kind of weird to conceptualize, but if you look at them, they'll have like a horizontal axis of symmetry. Which is due to like the nature of that cyclic group.
Does Q, if you add Q to itself enough times, does it repeat?
Yeah, it does. It'll go through every single point in the elliptic curve and then it'll repeat.
Okay, got it.
I'm not sure if it goes through like what?
It's like it's not a continuous, because you say every single point. So is it like a continuous thing? I guess it can't be. Like it must be discrete in some way.
No, it's basically, it's like will repeat on a cycle. I'm not sure if the cycle is minimum though, or minimal, as in like it might repeat certain points in going through all of them.
Oh, I see. Okay. Yeah, this is interesting.
It's also interesting because it doesn't seem, I guess, like the physical use of these types of geometry is very like obvious or like intuitive, but some of like, I don't know, just the fact that like elliptic curve cryptography comes out of this is like was surprising to me.
Yeah. No, yeah, that is really weird and kind of unexpected. I'm thinking about like ways, so like I'm thinking about like how I guess it's interesting to me because like I think humans actually do have a relatively good intuitive understanding of like spherical surfaces. I think like oftentimes when we talk about like spherical geometry or like hyperbolic geometry, we kind of assume that and I'm thinking now in terms of like our potential users, we may not like necessarily assume that like our users have that kind of like background to be able to reason about it. But if we make it something that's like easy to play with, like it's the surface of a sphere or whatever, then I think it rapidly becomes something that's much more easy to grok, which I'm curious like what other operations we can then like apply in a spherical space that I don't know, like may make exploration easier.
Yeah, I guess like it seems like there's a lot of transformations that would be easier because you can like rotate things without having to like there is that symmetry to a sphere. There also isn't to like a hyperbola, for example.
Yeah, that makes sense. You guys have any other questions? Cool, man. This was a great presentation. I really appreciate it. I think next week we have Robin? No, Robin already went. Next week we have Sarah presenting, so we'll see what Sarah has to say. But yeah, thanks a ton. We'll send out the recording as soon as this is, as soon as like Zoom decides to send it back to me.
Yeah, sounds good. I'll add my slides to the list.
All right, cool, man. Thanks so much.
All right, see you guys in a bit.
Stop this.